array nums and an integer k, and we want to return the k most frequent elements that appear in the array nums. We can return the answer in any order. So for example, we have this input array, 3 1s, 2 2s, and a single 3, and we want to return the 2 most frequent elements, right? So we know that the most frequent is, of course, 1. It appears 3 times, so we add a 1 to the output. The second most frequent is 2, so then we add a 2 to the output, and that's all we want. Now, if k was 3, of course, we'd add the last element. K is never going to be greater than the distinct number of elements in the input array, so that's good for us. And our input array is always going to be non-empty. So, for example, for each value, right, we're going to count how many occurrences it has. So, for example, 1 occurs 3 times, 2 occurs twice, and 3 occurs once. And then we can take this, basically this list of pairs, right? Then we can sort it in ascending order, right? So basically it's already sorted in ascending order, right? Because the most frequent is here, the second most frequent is here, the third most frequent is here, right? Now, of course, sorting it in the worst case, right? Basically, if every single value in here was distinct and we wanted the top k distinct values, we'd get a time complexity of n log n, right? But we don't necessarily need to sort the entire thing because we only want the top k frequent elements. So in another solution, we could actually use a max heap. So we would still do this whole operation where we count the number of occurrences of each value, and then we'd add each pair to our max heap. And the key of this max heap would, of course, be the number of occurrences, right? So the count, right? And then we'd pop from our heap exactly k times. So why is this more efficient? Well, we know popping from the heap. Well, first of all, when we initialize our heap, we're going to add this entire set. And there's a function called heapify, I think, that can do that in actually linear time, so big O of n times, so that's the good thing. And of course, we know we're only going to be popping from the heap k times. Each pop is going to take log n, and we're going to be doing that k times, right? So that's going to be k times log n, right? So that's a little bit better than n log n, at least as long as k is less than n, right? But it turns out that there's actually an even better solution. There's actually a solution that can be done in O of n time, linear time. So big O of n time and big O of n memory. But we are still going to be using this exact technique where for each value, like 1, we count the number of occurrences, like 3. So this problem can actually be solved in linear time if you use the algorithm called bucket sort. So when you first think of bucket sort, this is probably what you're going to think of. The way bucket sort is usually taught is that for each value, for example, 1, we're going to take an input array, right? This is our input array. This row is the indices, the index of the array, and this is actually going to be the value. So for example, for 1, we're going to go to the index 1, and in the value, we're going to put, okay, 1 occurs exactly once. Now we're going to see a second one, we're going to say 1 occurs twice, right? Basically, we're going to go through the input array, count how many times each value occurs, and then in our input array, put that count for that index, right? Map the value to the index, and then put the count of that value. So 1 occurs 3 times, 2 occurs twice, 100 in this case occurs once. Now this algorithm would be linear time if our input values, right, were bounded. For example, if we knew for a fact that every value was between 1 and 10, then we would know that the size of our input array is also going to be 10, right? But in this case, the values are unbounded, right? Like this could have been a million, and then the size of our input array would have been a million, even though the total input array size is only 6, right? We have 6 elements, but then that array where we actually store the bucket sort values is going to be unbounded, right? And also, we want the top k elements. This still isn't very clear of where exactly the top k elements are actually going to be. So in this case, this type of bucket sort doesn't work, but there's another way we can do it. So in this case, you can see for our array where we're going to be doing the bucket sort, the index I was using each value in the input array. For example, 1 was being mapped to index 1, right? And there we were storing the count. There's actually another tricky way that you can do it that will lead us to a linear time solution. So if we're pretty clever, this is what we're going to do. For the index, we're actually going to be mapping the counts of each value, and in the values, we're actually going to have a list of which values have exactly this particular count. For example, 100, right? We know that 100 occurs one time. So what we're going to do is for this position 1, we're going to say, okay, this value occurs only once. 100 occurs one single time. Which value, for another value in our input array 2, we see it occurs exactly twice, right? We can count that with a hash map pretty easily. And then we'll say, okay, this value occurs twice. So in the position 2, index position 2 of our array, we're going to add that value 2. 2 is the value that occurs twice. We see a last distinct value in our input array 1. We count it occurs exactly 3 times. So in this position, index 3, we're going to say, okay, there's a single value, a 1 that occurs 3 times. Now it's possible maybe we had a third 3, right? Maybe 2 occurs 3 times. In that case, we would actually have multiple values in this position, right? But in this case, we can see 1 occurs 3 times, 2 occurs twice, 100 occurs once. So they're all going to go in separate positions. And then, once we've taken every single input value and counted how many times each value occurs and then put it in the appropriate spot in this array, what are we going to do? Well, we want the top k values, right? The top k values that occur most frequently, right? So what are we going to do? We're going to start at this end of the array. We want all the values that occur 6 times. Why are we stopping at 6 though? Why don't I extend this array farther, right? 7, 8, 100, right? Why do the indices stop at 6? Notice something about our input array. Our input array is size 6, right? So that means if every single value in the input array was the exact same, the most number of times a value could occur would be exactly 6 times. So the cool thing about this new array that we're creating is it's bounded by 6, or well, technically 6 plus 1 because we do have a 0, but that's not actually necessary. But it's proportionate to the size of the input array, right? So when we're scanning from right to left, or however we do it, we're only going to be doing that. We can scan through the entire thing in linear time. Now in this case, we see 6, there's no values that occur 6 times, so we can't find our top k element in that position. We'll try the same thing with 5. 5, no values occur 5 times. 4, no values occur 4 times. 3, a single value. We're going to go through every value in this array. There's only a single value in this case, but we do see a 1 occurs. So to our result, we want the top k values, the top k occurring values. We are going to add a 1 to that. 1 occurs most frequently in the input array. So we add 1 to our result. We need 1 more, because I think we were looking for the top 2 values. K in this case is going to be 2. So now we're going to go here. Which values occur twice? A single value, and that value is 2. So we're going to add that to our output array. So now we've gotten the top 2 values, and then we can return this array. Now, why is this linear time again? Because remember, the max size that this array could possibly be is going to be about equal to the size of the input array, right? Because we could have a value, for example, 1 could occur 6 times. In that case, we'd have 1 over here. Now, what if every single value in the input array was distinct, right? That's another extreme. What if we had 1, 2, 3, 4, 5, 6? In that case, this position would be empty because no values occur 6 times, no values occur 5 times, 4 times, 3 times, or 2 times. Every one of these 6 values would go in this position at index 1. Reason being, each one of these occurs exactly once. So in that case, we'll have all 6 values concentrated over here. And that's still going to be linear time because, yes, we are going to be iterating through this entire input array, which is going to be big O of n. And then we're going to add another big O of n to that, right? Big O of n plus big O of n, because we're going to have to iterate through 6 values in exactly one position. So that's still technically linear time. Now we are creating this array to help us, and we're also going to be needing a hash map to count the occurrences of each value in the input array. So the memory complexity is also going to be big O of n. With that being said, let's jump into the linear time code. It's pretty easy once you can identify this trick. So We are going to use a hash map to count the occurrences of each value, or also the array. The special array that's going to be the same size as the input array is going to be called frequency. Basically, the index is going to be the frequency of an element or the count of an element.